Heather. I go to Ohio State University.
And restating, I go to Nebraska Wesleyan University.
I'm Arna Bhatani. I go to Vanderbilt University.
I'm Ryan Caddis. I go to Lawrence Technological University.
So for the past 8 weeks, our team has come up with 3 algorithms that allows a vehicle to successfully run 2 laps around the course, both the inner and outer lanes, within the lane lines. And we were limited to just using a camera and without using a GPS system or LiDAR. And then at the end, we evaluated the data using a customized evaluation system. And the vehicle that we tested with is the GEM E2 vehicle. It's a fully electrical vehicle, and it is equipped with drive-by-wire, which allows us to use code to control the steering, the brake, and the gas. And then the camera that we used is the Mako G319 camera, and it is RAW supported, which is the most important feature, and it took in all of the images while we were testing.
So this is the course we used. It's on LTU features in parking lot H. So some features of this course that make this research project unique are, firstly, you can see the sharp turns that our vehicle had to traverse. Then in the bottom left, you can also see the intersection and the yellow lines where our vehicle had to stop at and make a dead reckoning turn. Some challenges this course posed. You can see that there are a lot of yellow lines, and since our algorithms had to detect both white and yellow, these posed a problem because sometimes our camera would detect these and think it was the yellow line we had to stop at. And in sunny conditions, it also couldn't differentiate that well between white and yellow. And so the vehicle would go off course thinking it was meant to go to the yellow lines. And this is the course we ultimately tested on.
So here's the code architecture we developed. The architecture is developed for simplicity and modularity. So as you can see on the left up here, the stuff on the right, that's all drive-by-wire stuff. That's not developed by us. That's already on the car, and that's what the drive-by-wire system uses to control the car. But the interesting stuff is on the left. So that node up on top on the left, that is our lane following node. All it does is takes in the camera image, does whatever techniques it needs to do to produce an angle message or yaw rate message, which is passed on to the controller. Now right now it says lane blob detect, but the nice thing is it doesn't have to be blob detection. To test another algorithm, all you have to do is take out that node, put a new one in there, and you're ready to go. Now onto the controller, which is accepting the angle message. The controller determines whether lane following or stopping or dead reckoning is necessary, and it will take the angle message from the lane following node and package it into the proper twist message to then pass on to the drive-by-wire. Now the controller knows when to do dead reckoning or to lane follow from the detect yellow node on the left towards the bottom. Now the detect yellow node also takes in the camera image and looks specifically for the yellow line that we are required to stop at. So that will just send a Boolean message to the controller telling it whether it should continue lane following or to get ready to stop at the line and do our dead reckoning turn at the intersection.
So this is a filter we use in all 3 of our algorithms. It's median blur. So on the left, you can see that there's a lot of noise in the image, and on the right, you can see that it detects the edges way better and reduces the noise a lot and helps with all 3 of our algorithms.
So here's the first algorithm we implemented. This is the simple approach, the blob detection approach. So first we crop the image down just to the bottom right to minimize distractions and improve performance. Then we applied an HSV, after doing a median blur, we applied HSV filtering to filter out pixels by their hue, saturation, and value numbers. So we can pull just the white line out of the image based on its HSV values. You can see that in the mask over there, the contrast between the line and all the other stuff, the road, which is being ignored. Then we use blob detection and centroid calculation, which are OpenCV functions. You can see on the right image the red contour around the blob and the center dot, which is being shifted over of the blob. So essentially what the code has to do now, once it has the center point, the shifted center point, is to try to keep the center point in the center of the image by turning the car using the controller node. So you can see as it's driving along, it's trying to keep the center point towards the center of the image. And you can see how the blob detection works with the intricacies of the road as it jumps from crack to crack, from clump to clump of wet pixels.
All right, next we did Hoffline. I will first mention the middle line here that's being drawn out is a little bit shaky, and it's the more raw version of the average slopes of the Hofflines that are being drawn. We used Hoffline that utilizes all our median blur, as well as our HSV filtering for our mask to then pass into canny edge detection, which allows us to do our Hofflines. So the middle line is essentially there to give us a rough estimate of where our vehicle needs to go. We're averaging the slopes of the lines drawn out to then determine the direction and how quickly we can move in said direction for the vehicle. So the raw line is a little bit all over the place, and it gets dampened down to a more realistic factor for the vehicle to move. But it's also important to note that we have a very different cropping here. We take into account both the center line and the outer line, opposed to our blob detection, which only utilizes the outside line. Some things to note with the Hoffline for us is as it gains and loses the inside or outside line depending on which lane it is running in. It can make some sudden movements depending on if it loses one of those, especially if the number of Hofflines that are there present are few. Lastly, we also used Professor Nick Paul's Spring algorithm that was initially made for C++ and then converted to Python. Initially, we had some issue with getting it running at a fast enough rate to work on the vehicle, so most of the work done was to optimize and get it implemented into our architecture the same way that our previous methods were. They work fairly all right. We ran into a similar thing that the other team had noticed. The inside lane seems to work slightly more consistently. I feel that it is able to pick up the Hoffline slightly better as the lane lines approach closer to the vehicle itself. So you see that it kind of loses it and then picks back up as it gets close and then holds it better on those lines. Again, we have a different region of interest. This is a larger area that considers almost the entire image. We do crop out the top half, so we get less noise from the outside world, although this is a full image view that you are seeing here.
Vehicle testing, so we, as I mentioned earlier, the goal was to make it so that the vehicle could make 2 full laps around the course, but we also tested to make sure that the vehicle wouldn't touch any of the lane lines, and that more so that it wouldn't completely departure from the lane. And we encountered some challenges, but the biggest one was the weather. All the algorithms did work in the weather, under the weather conditions, only after we had to adjust prior to testing. And we also collected how fast the car moved around the course, and then the speed it went around the course.
So here are some of the challenges we faced. So first, you can see the shadow. There's a tree at the edge of the course that during the morning and evening would put a shadow across the course. And when we entered the shadow, we would lose these contour lines, and we were unable to continue lane following. So the solution our team had for this was when it lost the contour lines, we would continue at the same yaw rate. And this was less successful in the outer lane because as you can kind of see, we enter the shadow at more of a straight line compared to the inner line. So we would continue and we'd go off the course because there's a curve we had to follow that we just weren't making this turn. But in the inner line, this was more successful as we were entering the shadow at a curve already. So obviously we need to, there's further testing to be done to actually be able to navigate in the shadow as well as in the light. And then you can see 4 different images of just the course. So the top left, you can see how close the yellow lines were to the white lines, and during sunny conditions, the algorithm easily mixed up the yellow and the white and would go off course. And you can just see the cracks and potholes in the course. And when we tested under rainy conditions, it was good because it was overcast, but unfortunately because of the camera, obviously the rain streaks messed up the view, and also the rain streaks were sometimes confused for Hoff lines, surprisingly enough. And there's slide 2. Thank you. And so this is the Mako camera we have. Unfortunately, the lens isn't polarized, so you can see at the top there, that's the image we have without the lens. You literally can't see anything at all. But the quick fix we had was just to tape a sunglass on, and you can see that we can now view out of the camera perfectly.
Yeah, so as was mentioned before, for all of our runs, not just human or algorithm-based runs, we recorded the vehicle steering report message as a ROS-bag file, and the steering report has a lot of good information, but the thing we were most interested in was the vehicle speed. And we use that to make these charts here of a speed versus time graph. These specific ones are just for human drivers, but the important thing to notice is how a human controls the vehicle speed. Now you can see on the left over here, this is Enver's driving. At the very start of his run, he goes up to 8 miles an hour, which is 1 mile an hour over our set speed limit of 7. Then he goes under to correct, then goes and hovers around 7. Then the second lap, he does pretty much the same thing. He goes up past 7, then tries to overcorrect. Then you can see my performance on the right top. You can see I start off pretty slow, just barely going over 5, then sort of ramp up as time goes on during the lap. And I also do that for the second lap. And you can see on the bottom right, that's Heather's run. You can see she gets up close to 7, then overcorrects, goes down, and then starts hovering around 6.5. And she does that for the second lap. So you can see that the human drivers have a harder time controlling their speed over time when compared to the lane following algorithms. Now, the first thing you need to notice is that these lane following algorithms are running at a much slower speed. They couldn't really keep up with the human drivers, but all the same. The important thing to notice is all these bumps and troughs here are the result of the algorithms reacting to every bump and crack and inconsistency in the road. So the important thing to notice about blob on the right bottom is that it's fairly smooth except for right around the start of the lap each time when it would have to go over a bump in the road. But it would remain fairly smooth and fairly consistent at the set speed of 2.23 miles an hour. Then over here on the left we have Hoff, which was a less reliable algorithm for us. And you can see it could speed up to 2.23, then it would have to make a quick turn as it was reacting a bit slower, so it's a bit more jagged than normal. And you can see the spring algorithm on the right top is also doing the same speed up, slow down, because it also relies on Hoff lines.
Our testing results overall, we have divided up into our blob, Hoff, spring methods, as well as our human drivers, in addition to the inner and outer lane performances. We do have percent success rates here. I would like to mention that these are done only over our recorded ROSBAG files from the previous 2 days. So we're very limited on that data currently, but we'll be expanding that as we go on to get more accurate percentages. Alongside with that, our fastest overall speed was the blob method, the blob detection on the outer lane. And we have some pretty consistent times for the outer lanes and the inner lanes, and as you would expect, since there's less distance traveled on the inner lanes, our times are also lowered. It is very clear though that our algorithms are performing as intended to hold the speed and not be inconsistent as human drivers are. As you see, we go between roughly 2 and 3.2 meters above or below the speed limit, with our lower threshold being 1.5 miles per hour, whereas human drivers are going over for most of the time, but anywhere from roughly 45 meters to 18 to 20. The number of lane line touches that we had, for most of these, they were related to our dead reckoning turns. They were not quite as optimized as we would have liked to have at the very end, but most of these touches are clipping a lane line as we're turning into the lane and not actually lane keeping itself. And there was only 1 lane departure, and that was our Hoff on the inner line. Anything else? No? Okay.
In the end, all of our algorithms had at least 1 successful run through the course, whether they were altered due to the weather and lighting conditions or not, but we found that there wasn't 1 algorithm that worked completely untouched in any of the weather conditions, and we also found that we didn't have 1 algorithm that worked best for both inner and outer lanes. We found that the spring worked best for the inner and that the blob detection worked best for the outer. And so in the future, the hope is that the algorithms would be improved so that they would be much more accurate, with more successes during